Welcome to today's Explainer. I am absolutely thrilled you're joining us because we are diving headfirst into a high-stakes industrial race happening right now in modern shipyards. We're looking at a showdown between three incredibly powerful steel-cutting technologies: the plasma arc, the laser, and the water jet. Building a massive modern vessel means shaping thousands of tons of raw steel, and it has to be done with absolute precision. Using the wrong tool for the job? Well, it doesn't just cost a few extra bucks, it can literally cost massive amounts of time, millions in rework, and totally compromise the quality of the ship itself. So let's jump right in and see how modern manufacturing tackles this incredible challenge. Okay, picture this for a second. Imagine a starting line. You've got three different cutting heads, lined up, hovering just millimeters above three identical steel plates. The starting gun fires, and boom, they race across the metal. Now, human nature kind of makes us want to pick a winner, right? We naturally expect that one of these cutting technologies is just the undisputed champion, the single best way to cut steel that makes all the others obsolete. So which one actually crosses the finish line first? Which one leaves the absolute cleanest cut?
Well, here's the twist that completely subverts what we'd expect. If that steel plate is thin, the laser shoots ahead and wins purely on speed, no contest. But swap that out for a heavy, thick steel plate, the laser really struggles, and the heavy-duty oxy-fuel cutter absolutely dominates the field. And meanwhile, the water jet is just quietly slicing through its plate with zero sparks, zero smoke, and absolutely zero heat. The crucial takeaway here is that there is no single best cutting method. Every single technology has a specific domain where it wins and a domain where it completely strikes out. Which brings us to Section 1, the framework, and the 5 rules of evaluation. To navigate this incredibly complex showdown, shipyard engineers don't just, guess. They use a highly structured framework. It all comes down to evaluating 5 critical variables: plate thickness, cut speed, edge quality, heat input, and running cost. And as we break these down, you'll see that no single method gets a perfect score across the board. Oxy-fuel handles massive thickness, but totally fails on heat input. Plasma, it gives you amazing speed, but sacrifices edge quality compared to a laser. The laser gives you perfect edges, but the running costs are super high. And the water jet gives you zero heat input, but you're paying a premium price for a slower speed. Building a ship is literally a masterclass in calculated optimization. Let's move into Section 2, the battlefield, matching the tool to the task. So how does this matrix actually play out on a real ship? When production planners zoom out to the macro level, every single piece of steel gets assigned its own specific cutting weapon. First up, we've got oxy-fuel. This is the heavyweight bruiser of the shipyard. When you're dealing with heavy plates, we're talking the ultra-thick keel sections at the very bottom of the ship, the stem bar at the bow, or the massive rudder stock, oxy-fuel is your undisputed winner. It works by preheating the steel to its ignition temperature, and then it blasts a high-pressure jet of pure oxygen right through it. The steel literally burns in an exothermic reaction. It is incredibly effective on thick plates and surprisingly economical to run. Next up is the plasma arc. If oxy-fuel is the heavyweight boxer, plasma is the track star. It wins on pure speed for medium-thickness structural plates, which actually make up the vast expanses of the ship's general hull. Plasma works by ionizing a gas into a plasma jet that reaches temperatures up to an astonishing 20,000 degrees Celsius. Crazy, right? It cuts through the steel by melting it rather than burning it. It's way faster than oxy-fuel on thinner plates and leaves a much narrower cut, which means way less waste. Then we have the laser. Think of this one as the precision sniper. The laser takes over when edge quality and absolute perfection are just non-negotiable. We are talking about highly complex structural brackets, intricate pipe penetration rings, and critical connections that require extremely tight tolerances. The laser uses a highly focused light beam to literally vaporize the steel. It is intensely precise, but, as you might guess, it costs significantly more per meter to run than plasma. And finally, we have the water jet, the cooled cutter. This is a highly specialized tool deployed for composite materials, high-strength alloys, and scenarios where introducing heat is strictly prohibited. It relies on an ultra-high-pressure stream of water mixed with abrasive particles. It cuts without generating any heat at all. But that begs a pretty big question. Why are engineers so obsessed with avoiding heat? Why fork over the high premium to run a laser or a water jet in the first place? Let's uncover exactly why in Section 3, the invisible enemy, the heat-affected zone. To really answer that, we need to zoom all the way in, from the macro level of the entire ship down to the microscopic level of the steel itself, to face the absolute biggest enemy in thermal cutting.
Every single thermal process creates what engineers call a heat-affected zone, or haze for short. This is the region right next to the cut where the extreme heat has fundamentally changed the steel's microstructure. Inside the zone, the steel's mechanical properties actually become different from the base material. The intense heat can cause distortion, it can lock in residual stresses, and it can literally alter the strength of the metal. If you're building a ship designed to take a pounding from ocean storms for 25 years, changing the microstructure of your critical structural steel is a massive, massive problem.
And this brilliantly illustrates the real difference between our cutting technologies. Look at the extreme contrast in the has size between these methods. Oxyfuel, because it relies on that massive, continuous exothermic burn, produces the widest and most disruptive heat-affected zone by far. The laser, because it vaporizes the steels so incredibly quickly and precisely, leaves a very narrow has. And the water jet, because it is a completely cold cutting process, it leaves absolutely zero has. The metal's microstructure remains perfectly 100% intact. So here is the bottom line. Preserving the exact structural properties of the metal often far outweighs the higher running costs of the cutting machine itself. An engineer will gladly pay the premium to fire up a laser or a water jet for a critical precision part, simply to avoid the massive distorting heat-affected zone that an oxyfuel torch would leave behind. It's an incredibly calculated trade-off between the immediate cost of the cut and the long-term integrity of the ship.
Let's pull it all together in Section 4, the resolution, driven by the digital model. So with all these competing variables, thickness, speed, edge quality, and the dangerous heat-affected zone, how does a shipyard actually manage this complex showdown day in and day out? Well, it all comes down to the digital model. Modern shipyards rely on a massive integrated 3D database called the Ship Product Model. This model contains every single piece of data about the ship. It feeds part geometries automatically to the production planners. The software evaluates the exact requirements of that specific part, its thickness, its required tolerance, its heat sensitivity, and then it explicitly assigns the optimal cutting method. There's no guesswork on the shop floor. The entire workflow is driven by perfect digital data. Which brings us right back to the core takeaway of this entire explainer. There is no single best cutting method. The real skill is matching the method to the job. Whether it's deploying the heavyweight oxyfuel, the speedy plasma, the sniper-like laser, or the flawless cold-cutting water jet, modern manufacturing just doesn't rely on a single magic bullet. It relies on a carefully orchestrated matrix of perfectly matched technologies, all working in total harmony to bring a massive digital blueprint into the physical world. But wait a second. As amazing as all these cutting tools are, they actually only solve one part of the puzzle. They just give us perfectly cut, flat pieces of steel. Take a look at literally any ship in the water. The bow, the stern, the hull, almost nothing below the waterline is actually flat. So, if these incredible machines are just cutting flat plates, how on earth do shipyard workers bend solid, thick steel into the complex, double curvature hydrodynamic shapes required for a ship's hull? Well, that is a whole different ballgame. Thanks for exploring this high-stakes industrial showdown with me today, and as always, keep questioning how the world around you is built.